Today's learning goals. First, intuitively recognize the probability density function to describe the distribution of continuous random variable. Second, understand that the probability that contains a continuous random variable assumes a single value is always zero. Third, understand normal distribution. Fourth, understand the properties of a normal distribution. Okay, so today we're going to start to learn continuous random variable. And make an introduction of the common continuous random variable, which is normal distribution. So first of all, let's go over what continuous random variable are. Okay, continuous random variable that a random variable that can assume any value contained in one or more intervals is called a continuous random variable. That means for a continuous random variable that in the number axis, there should exist at least one interval that the random variable can be any value in this interval, right? Okay, here are some examples of continuous random variable. First, the length of a room is a continuous random variable, right? Because the space is usually continuous. Okay. Second, the time taken to commute from home to work, for example, could be 10 to 20 minutes, is also a continuous random variable because time is commonly regarded as continuous, right? Okay, there are some other examples. We can have a look after the class. Okay, so the question here is how to describe a continuous random variable. We cannot use a probability distribution table, right? Because we cannot list all the possible values that continuous random variable can be. So the probability distribution table is not applicable here. Okay, let's use an example to illustrate how we describe a continuous random variable. Okay, the example says, even though a fast food chain might advertise a hamburger at weighing a quarter pound, you can well imagine that it is not exactly 0.525 pounds. One randomly selected hamburger might weigh 0.23 pounds, while another might weigh 0.27 pounds. What is the probability that a randomly selected burger weighs between 0.20 and 0.30 pounds? That is, if we let X denote the weight of a randomly selected quarter-pound hamburger in pounds, what is the probability that X lies in this interval between 0.21 and 0.30? Okay, so here, the random variable X is the weight of randomly selected quarter-pound hamburger, right? So X here is continuous random variable because weight is commonly regarded as continuous. So how to describe the continuous random variable here? Okay, suppose we have chosen 100 hamburgers. We have a 100 sample points here. Then how we describe the probability distribution? We'll use a technique called histogram. Yeah. We'll learn the detailed methods to draw the histogram later in this class. So here, I'll just make a very quick introduction to histogram. So first of all, we list all the 100 sample points here, and then we calculate the range of the data points, which is the maximum value minus the minimum value, which is 0.426 minus 0.111, which is 0.315. And then we use some number of classes Okay, for example, we choose to use, for example, 5 classes. And then we can calculate the length of each class, which is a range divided by number of classes, which is approximately 0.063. And then we calculate the frequency of each class, as well as the relative frequency. Okay, first we list all the classes. Okay, first column is class. So the first class would be 0.111 to 0.174. Second class would be 0.174 to 0.0. Second class 0.174 to 0.237. Third class would be 0.237 to 0.3. Fourth class 0.3 to 0.363. Last class 0.363 to 0.426. Okay, then we calculate the frequency of each class. Okay, we start to check each value one by one. Okay, so the first class is 0.111 to 0.174. 0.174 should be here, right? So the first class, the frequency of the first class is 1, 2, 3, 4, 5, 6, 7, 8. And the second class is to here, right? So how many numbers are there? 1, 2, 3, 4, 5, 6, 7. So 27. Okay, the third class is to 0.3. 0.3 is here. So basically we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, 43. Okay, next one is 0.3 to 0.363. 363 is here. So we have 10 here. And the last class, we only have 2 sample points there. Okay, so this is the frequency for each class, and then we can calculate the relative frequency. Which is 0.08 0.27, 0.43, 0.10, 0.02, right? Okay, now we have the classes and the relative frequency for each class, and then we use these two rows to draw the histogram. Okay, in the histogram, the x-axis is your random variable, and y-axis is relative frequency. Okay, next, the first class is 0. Okay, how many classes are there? 5, right? 1, 2, 3, 4, 5. Okay, first class 0.111 to 0.174. The next class is to 0.237. Next class is to 3.300. Next class is to 0.363. Next class is to 0.426, right? And the relative frequency, first one is 0.08. The next class relative frequency is 0.27. Okay, next one. 0.43. Next point is next class is 0.10. Next class has a relative frequency of 0.02. Okay, so this is called a histogram that illustrates the distribution of these data. As we can see here, most of the data are concentrated in the center, right? That is between 0.237 to 0.300, right? Okay. In this histogram, the class interval we choose. Okay, first of all, number of class we choose is 5, right? And class interval we choose is 0.063, right? We can increase the number of classes. As the number of classes increases, the number of class intervals decreases, right? Because the range are fixed. This is called range. The range are fixed. So as the number of classes increase, the class interval decrease, right? And if the number of classes is very large, the class interval is very, very small, right? And if the class interval is small enough, okay, for example, when the class interval is small enough, the histogram, the bars, becomes a function curve like this. And actually, this function is called the probability density function. And for continuous random variable, we use probability density function to describe its probability distribution. In the probability density function, the y-axis is no longer the relative frequency or relative or probability. It's the value of the function denoted by fx. The x-axis is our random variable x. In this probability density function, the area between any two values, for example, here we have an a and b. The area between any two values a and b denotes the probability of x falls in this interval. This is the meaning of the probability density function. Understand? For example, we have 0.20 here and 0.30 here. The shaded area here denotes the probability of x falls within this interval. Understand? Okay, let's see some of the properties the probability density function has. So first of all, as I said previously, if this is a probability density function, PDF, so the area between any two values, a and b, denotes the probability of x falls within this interval. Okay, so here, this shaded area denotes the probability of x in this interval at a and b. So because it is a probability, so the shaded area is always between 0 and 1, right? Because any probability is above 0 or equals to 0 and equals to or less than 1, right? And the whole shaded area under the curve and above x-axis is always 1. Why? Because it's the probability of x lies in minus infinity and positive infinity, right? This area corresponding to the probability of x more than negative infinity and less than positive infinity. So the whole shaded area here is 100%. Any questions? All right, next, you should pay special attention here. The probability that a continuous random variable x can assume a single value is always 0. This is very important because, as we said, if this is a PDF, probability density function, the area between any two values stands for the probability of x lies in this interval, right? Once the upper limit and the lower limit becomes 1 point, see here, for example, we have a point of 66.8. When the upper limit and lower limit becomes 1 point, the probability here is actually 0. Why? Because we have no area here. This is a thin line. There's no area. Area here is 0. So the corresponding probability is 0. Understand? Okay. Following this, we can deduct that for any continuous random variable, the following statement holds, which is the probability of x equal to a or more than a and x equal to b or less than b equals to x the probability of x more than a and equal to or less than b, which is also equal to the probability of x equal to a and more than a and the x less than b, which is also equal to the probability of x more than a and less than b. The four statements here are all equal, no matter we have put a quality sign here or not. Understand? Because at a single point, a continuous random variable being a single point is always zero. Okay, this is very important. All right, any questions? No? Okay, to summarize what we have discussed so far. Okay, assume x is a continuous random variable. The probability density function of x is fx. Then we have, first one, the probability of uppercase x, which is our random variable, is equal to or less than the lowercase x, which is any real number. Is the integral of fx between minus infinity to x. Okay, if we draw a diagram, if we draw the function of PDF, it tells you that, okay, for example, this is a PDF. Okay, the first statement actually say this thing. Suppose we have a lowercase x here. The probability of x being equal to or less than x is this area, right? It's the whole area on the left-hand side of x. So this area is denoted by an integral. Okay, so this is the first statement. The second statement is that for any two given values, such as a and b here, suppose a is the lower limit and b is the upper limit. The probability of x lies in this interval corresponding to the area of this curve and x-axis, which is denoted by integral from a to b of fx. Okay, the third statement is actually tells you for a continuous random variable, so x being any single value k is always zero. It's very important. Okay, and based on this, number 4, all these 4 probabilities are equal, as we have discussed before. You understand? Any questions? Okay, no? All right, let's continue. Okay, and you still remember that we discussed the 3 special discrete distributions in our previous lessons, right? So similarly, in this unit, we'll learn one continuous distribution, which is called normal distribution. Okay, so first of all, let's figure out what normal distribution is. Okay. By definition, if x is continuous random variable and the PDF of x has this form, then x is yields to a normal distribution, denoted as x yields to normal distribution. There are 2 parameters in normal distributions. First one is its mean. The second one is its variance, sigma square. Okay. You don't have to remember this formula. Okay, this formula you will learn it in your university study, no matter how you approach the statistics or probability. You will learn this in your university study. Currently, you only have to have an intuitive feeling that if the PDF of X has this form, then X yields to a normal distribution. And there are two parameters in the normal distribution, which are mu and sigma square, right? Okay, so next, for the properties of normal distribution, you need to remember all the properties that normal distributions have. Okay, for example, first of all, you need to know that the probability density function of the normal distribution has a form similar to this. It's a bell-shaped and symmetric curve. This is the probability density function of normal distribution. But for a normal distribution, it always have a probability distribution function like this. And symmetric axis is always its mean, which is mu. Okay, so like all other continuous random variable, the total area under the curve is 1.0, right? Because it stands sum of all the probabilities here. Okay, the second one, the curve is symmetric about the mean. Okay. The third, the two tails of the curve extend indefinitely. This is the three important properties of the probability density function for a normal distribution. Okay, any questions? Okay, let's go over them one by one. Okay, first, okay, let's go over the properties of normal distribution. Okay, one by one. First, the total area under a normal distribution is 1.0. Like all other continuous random variable, if this is a PDF, the total area under the curve is always 1, right? Okay. The second, because the probability density function of a normal distribution is symmetric about its mean. So on the left-hand side of the mean, this area is 0.5, right? And on the right-hand side of the mean, the area is also 0.5, right? So on each side, the probability is always 0.5. That means 50% of the total area and the normal distribution curve lies on the left-hand side of the mean, and 50% lies on the right-hand side of the mean. Understand? Okay. This next rule is called 68, 95, and 99.7 rule, which means if X yields to a normal distribution, n mu sigma square, we have the following equalities. First, the probability of X lies in mu minus sigma to mu plus sigma is always is approximately 68%. Second, the probability of X lies in mu minus 2 sigma and mu plus 2 sigma is approximately 95%. Third, the probability of X lies in mu minus 3 sigma and mu plus 3 sigma is approximately 99.7%. And on the right-hand side, there's a diagram illustrate this principle. This is called 68, 95, and 99.7 rule. This rule is very important in our practical, everyday practical problems. Okay, that means most of the data are concentrated at the center, right? Most data concentrate in the center. This is a very important property of the normal distribution. Okay, any questions? Okay, next, you need to be able to interpret the mean and standard deviation for a normal distribution. Actually, the mean decides the relative positions of this normal distribution. The standard deviation decides the shape or dispersion of the data. Okay, for example, let's look at the first diagram. There are three normal distribution curves here with the same mean but different standard deviations. Okay, same mean means the relative positions of the three distributions is the same, right? The symmetric axis is the same. For a larger mu, that means the dispersion of the data is large. For example, when mu is 16, the curve is more flat and fat, right? For smaller mu, the curve is actually thin and tall, right? Because when mu is small, the dispersion of the data is small, so the curve becomes thin and tall. Otherwise, the curve becomes fat and flat. Understand? Any questions? Okay, next let's see the second diagram. The second diagram illustrates that for these three normal distribution curves, they have different means, but the same standard deviation. Okay, if they have the same standard deviation, means the dispersion of the data is the same. So the overall shape of the curve is the same, right? But they have different means. For larger means, the curve is on the right-hand side. That means the overall level of the data is larger. For smaller means, that means the overall level of the data is small. So the curve is on the left-hand side, right? So basically it tells you that if all the curves have the same standard deviation but different means, then the shapes of all three curves are the same, but with different position. Positions are decided by their mean. Understand? Okay, I'll explain this a little bit in Chinese again. Okay. 好，对于正态分布来说啊，mu 是它的均值，对不对 ？mu 决定整个图形的位置，mu 越大，图形这个位置越靠右。sigma 决定它的分散程度 ，sigma 是标准差，对不对？标准差决定了一个数据分布的分散程度，所以标准差越大的话，说明什么？数据是不是越发散？越发散反映在图形当中是越矮越胖，对不对？如果越集中的话，mu 如果越小，就是说标准差越小，说明这个数据波动越小，对不对？波动越小的话，是不是数据更容易集中啊？更容易集中的话，数据应该集中在均值周围，对不对？所以它又瘦又高，这个需要大家记住啊。mu sigma 决定了两个图形的位置和形状。好 ，this is today's knowledge, all knowledge for today.